Okay, good morning everyone. Today we're going to talk about this very interesting paper. It's called Inductive Representation Learning on Large Graphs. And it's published in 2017 in NIPS by Hamilton and et al. So again with the agenda, we're going to have four things: the problem, the motivation, the methodology, and also the experiments and results. So first off, let's go to the problem. So what's the problem of graph representation? So let's say we have a graph with some vertices and edges. And each node in the graph contains some attributes or contains some information. The question is, how can we represent it in a way that allows us to do ML with it? And should we use an adjacency list? So the thing is, no, we can't use adjacency list because let's say there's a graph of 5 nodes, it'll be 5 by 5. And let's say it's a graph of 1,000 nodes, then it'll be 1,000 by 1,000, right? And it grows, as the graph grows. So we can't use an adjacency list. So what we can do, we can use node embeddings. What node embeddings is transforming that high dimensional amount of information into a low dense embedding space. And this approximates the similarity of the original graph, the embedding itself. So let's say for this graph, we can code it into like this. So the similarity of node 1 and node 2 is basically the dot product of 1 and 2. Okay, so that is embedding. This is just an example. So similarity is 0. Yeah. Okay, so yeah, we want nodes that are close together to have a dot product of a high value, and nodes that are far apart to have a dot product of low value. Okay, so that's embedding. So if we have this embedding, what kind of task can we use it for? First, we can use it for node classification. So we can classify, let's say we have an unseen node, we can classify whether this node belongs into which of the areas or which of the categories in the whole graph. So maybe the graph has a lot of categories, like maybe you're on Reddit and you're talking about maybe Malayan, and then if this node is some text to do with Malayan, you'll actually classify it to that subreddit or something like that. So when we move on to clustering, so it wants to know when these nodes belong in the whole graph. So where should I put this node? Yeah. So that's what you can do with embedding. And lastly, link prediction, because you can know how similar one node is from the other, you can do link prediction. Okay. So there's another problem to this representation problem, which is, let's say the graph changes tomorrow. Now we are in an interconnected world. So let's say everybody use Instagram, right? Okay, and you have many followers. Today you might follow somebody, and tomorrow you might follow another person. So this social network graph keeps changing, but the problem is previous works can't encode this new node in the graph without regenerating the embedding for the whole graph. So let's say today I'm following Huang, right? Tomorrow I don't like Huang, I'm going to unfollow him. So I need to change the embedding for myself and Huang if we have this new paper. If not, we have to change the embedding for everyone. Okay? So that's where our motivation lies. So the motivation of this paper is that graph changes quickly in social network or other networks. And in previous works, such as Deep Walk and Line, they only focus on generating embedding for a single graph. The embeddings cannot be quickly generated for unseen nodes, and it cannot scale to high throughput. Means that it cannot be used in production ML system if the graph keeps changing. So we need to move from a transductive embedding generation to inductive embedding generation. So what do I mean by transductive and inductive? So transductive is basically statistical inference, and it's like most of the machine learning tasks. Basically, you have an observed set of data with labels, and you run it to train the model and apply it to test cases. That is transductive. So what inductive is there is a general set of rules. So let's say for a graph, there's a general set of rules for all graphs, which is that they have some degrees, and they have some information in that node itself. So this is general to all graphs, and we can use that. So this is like text attributes and node degrees. So now I'm going to talk about the algorithm, which is called graph stage. And this is the method they proposed. So let's say that, that this algorithm has 3 steps, which I'll explain later in detail. First is the sampling of the neighborhood. We aggregate the features from the neighbors, and finally we predict whatever task we want to use it on. Okay? So let's start with the algorithm. I'm going to break down the algorithm so that we can understand it easily. So we start with you start with an input vector for all nodes, which we call H0. H0 for a specific vertex. And this H0 is basically the input vector. Let's say we now want to find the embedding for the red node here. I don't know why it's not right here, but it's red on my screen. So it's supposed to be red node. We want to find embedding for that node using graph stage. So in the first iteration, this is the iterative algorithm. For the first iteration, k equals to 1, we want to aggregate all the H0s of the neighbors to obtain H1 of neighbor V. Okay? So we aggregate all the green nodes into H1 neighbor of the red node. Okay? So now we have the neighbors. Then we feed the aggregated H1 NV with the H0 V of the node we are trying to find, this one, into a fully connected layer with a non-linear activation function. And then we obtain a vector for this node. So because this vector is not of norm 1, so we try to normalize it with L2 node. Okay? And again, this is done for the rest of the graphs because you can't have one without the other. Okay? So the rest of the graph will do the same thing. So if this is the red node, you take the neighbors and you aggregate and you get the embedding for that node. So the next iteration, k equals to 2. So all the graphs have some H1 already. Okay? And now we take the neighbors of the red node again, but this time we aggregate all the H1s. This is the next level. Okay? So once we aggregate all the blue nodes, we have H1, H2 and V. And once we have H2 and V, we can put it together with H1V of the node we're going to find to get H2V. Yep. And then we can normalize H2V again to L2 norm, with L2 norm. So let's say our algorithm ends at k equals to 2. Then H2V is the embedding for that node V. And we want to do this for the rest of the nodes as well. You can't do it for one node and not with the other because you need the H1V and H2V to continue of the rest of the nodes. Yeah. So that's the algorithm. So to put it in a pseudocode, it's like this. We have input vectors for all nodes. For k equals to 1 to k, for every node we create H0, okay, H1 NV for every node. We create H1V for every node, and then we continue H2V, H3V, H4V, how many Ks we want depending. Yeah. And once we finish the K, that is the embedding for that node itself. So as you've seen, we have a non-linear activation function. So for that fully connected layer, we need some kinds of weight. So we need to learn that weight. There is a way to learn it that's called unsupervised setting. Means that the weight is just basically bringing nodes that are close together on the graph to have a bigger dot product. Whereas nodes are far away apart on the graph has a smaller dot product. So if we optimize with this loss function, basically we are doing that, which is bring similar products, closer nodes together and further nodes apart in that embedding space. Okay, and for a supervised setting means that you want it to work on some specific task. You can change this loss function to some function you use for your task. Okay, so that's called supervised settings in the author sense. And lastly, you can use different aggregators. So the aggregators are basically how you put neighbors to aggregate neighbors. So one thing is you can use a mean aggregator. Means that you can just take the eliminized mean of the 3 neighbors. Okay, that's one way. You can use the LSTM aggregator, which is you feed the 3 nodes in any order into the LSTM to get the representation for the neighbor of that node. And lastly, you can use a pooling aggregator, which is a element-wise max of the neighbors followed by a fully connected layer. Okay, so there's a few aggregators that you can use, and this is where the deep learning part comes in. Okay, the thing is, because there could be so many nodes in the graph or so many neighbors, what the authors choose to do is they sample a subset of fixed number of nodes to use as neighbors. Okay, so that's one way they can reduce the complexity. If not, if this graph is fully connected, then the complexity of this for every iteration is V. So then you have a very complex algorithm which you can't run. That's why they need to have fixed the samples. So what's the experiments and the results? So the experiment for this is, there's a few. So this task is not limited to this, this problem is not limited to this task, but these tasks are just a sample of a representation of tasks that can be used for the embeddings. So one is classifying academic papers into different subjects using the Web Science dataset. These are citations from papers from 6 different fields of biology from 2000 to 2005. It has 300,000 over nodes and a degree of 9.15. Next is classifying Reddit posts belonging to different communities, subreddit. So how do we know which node is in which Reddit? The comments in each post in 50 communities are gathered from September 2014. And there's 200 over 1,000 posts with a degree of 492 if, let's say, a post reference another post. Yeah. And lastly is a classifying biological protein-protein interaction. This is more for bio, and yeah. So we can see that GraphStage actually does pretty well in this aspect. Different aggregator has different scores, but mostly it does pretty well with the LSTM aggregator, because this is interesting. So the authors actually propose that aggregators should be symmetrical. It means that no matter which order you put the nodes in, it should come up the same. But somehow LSTM, there's an order to LSTM, right? So if you put it in this way, the output vector will be different compared to if you put the 3 nodes in a different order. So although they said that, they say they don't see much difference with LSTM if you put it in different order. So you can actually use LSTM as well. So you can see that the GraphStage obtained the highest F1 for most of the tasks. Actually, for all the tasks, yep. Yeah. And if you are talking about training inference, GraphStage actually has a very fast compared to deep work in terms of inference. And we're talking about inference, so if we have a million test cases, the inference will be a lot more. So training is just one time. So that's the training time doesn't really matter, but the inference times matter a lot more, because if you have a lot of inference data, then that's going to be huge on the computation power. So next thing is the neighborhood sample size. As the neighborhood goes up, what is the F1 score? So we can see that at a sample size of 25 neighbors, we can actually get pretty good F1 already. It starts to slowly, gently increase. So from sample size of 0 to 25, the F1 score increased a lot. So you should use more than 25 samples of neighbors if you want to use GraphStage. Yep, and that's all I have to say today. So GraphStage is actually really helps in generating embedding for unseen nodes, and it actually does well with all these tasks of classification and clustering. Yeah. Thank you.